In this video, we are going to talk about salt hydrolysis. This means that when a salt is put into water and dissociates, sometimes a portion, either the anion or the cation of that salt, can actually affect the pH of the solution because it can act as a weak acid or a weak base. So we're going to look at some ionic compounds to understand how this could be, in some cases, possible and how to recognize when it is possible. So for each of these salts listed, we're going to think about what ions the salt breaks into in water. And think about each ion, can it combine with water to act as a weak acid or base? So the first example here we have is sodium nitrate. When sodium nitrate goes into water, it dissociates completely because sodium and nitrate are both on our list of soluble ions. So you will not see any intact sodium nitrate. And in fact, all these salts listed, they're all going to dissolve completely because they've got nitrate or sodium on them somewhere. We're going to look at this and we're going to think about, okay, could either the sodium or the nitrate interact with water to make a weak acid or base? In other words, could the sodium or the nitrate on their own be a weak acid or base? Well, sodium, if it were to combine with water, would make sodium hydroxide. But sodium hydroxide is not going to reform because it's a strong base. And we know that strong bases never exist as a complete entity in the solution. They are 100% dissociated. So this means that we won't have any of the strong base formed, and so this won't affect the pH. If nitrate interacted with water, it would make HNO3. This is nitric acid, which is on our list of strong acids. So that means there will not be any HNO3 forming. Therefore, because the NaOH and the HNO3 will not reform, this will not impact pH, and so we will not have salt hydrolysis happening here. All right, so let's look at the second one, C5H5NHNO3. Now you might think, wow, this is a big compound. How would I ever know how this thing is going to break down? But I recognize within this compound the NO3 polyatomic ion. And so even though the other part is not something I recognize, you always look for the basic ones. Sodium, nitrate are two very common ones that you're going to see actually in pretty much all these examples. So when this salt dissociates, you're going to have two ions, C5H5NH, and I'm going to guess that is a plus because it's combined with nitrate, which is minus. Well, if this were kind of like in the previous example, if nitrate were to combine with water, it would make nitric acid. That's a strong acid, so that is not going to be formed. And so that is not going to have an effect on the pH. On the other hand, this cation that I do not recognize could do something interesting. It's not on my list of strong acids or bases, clearly, because I don't recognize it as a species I've seen before. So that means if I put it into water, it can do something rather interesting. Since it's a cation, it can interact with water and pick up hydroxide. So it's going to react with water. It's going to pick up hydroxide to make it NHOH, leaving behind hydrogen. So that means if I put this species, C5H5NH+, into water and it interacts with that water, it's going to take hydroxide from the water, increasing the concentration of H+ in the water. And if you increase the concentration of H+, this will increase and it will decrease the pH, or in other words, make the solution acidic. So this salt that we started with will make the pH of the solution lower. Let's move on to the next example. We've got calcium nitrate. When this thing ionizes completely in water, because ionic compounds do, especially when they contain soluble ions, we'll have calcium and 2 nitrate ions. I think we've established now that the nitrate is not going to have any effect on the pH no matter what, so we're just going to leave it at that. The other species to consider here, calcium, it's going to add hydroxide to it. So I have to think, well, is calcium hydroxide on my list of strong bases? So this is a strong base. It will not form therefore, calcium nitrate will not impact the pH of the solution. So this would be a neutral solution. Our next example is sodium nitrite. So we got something different here. Instead of NO3, we have NO2. When this salt is put into water and it dissociates, which it will because sodium's always going to make a soluble salt, we've already established, I'm writing NO3 out of habit, but that is not what we have here, it's NO2. We've already established that sodium is not going to affect the pH because NaOH is not going to form because it's a strong base. But we have this NO2, which would form nitrous acid. It is not, it is a weak species. So if we put NO2 into the water, we will get a weak kind of response. The NO2, some of it will combine with water to make nitrous acid, which is a weak acid, which will then increase the amount of hydroxide floating around in the water. So it will increase the concentration of hydroxide, which will increase the pH and make this a basic solution. All right, our next example is sodium acetate. Oops, I want to use black. C2H3O2. When we put sodium acetate into water, it makes sodium. Again, we've established that's not going to have an effect on the pH of the solution, but we got C2H3O2. That acetate ion is not, the acetic acid is not on our list of strong acids or bases. And so we can think about what happens to this ion when it goes into water, when it interacts with water. So if this interacts with water, since the ion is an anion, it is going to, or has the potential to, pick up a hydrogen from the water, which means that there'll be more hydroxide floating around in the solution. And when you have more hydroxide, that increases the pH and makes the solution more basic. And again, just to reiterate, the reason we're not paying attention to sodium is if we put sodium in water and we tried to say, okay, well, that will make sodium hydroxide. Well, that reaction just is not going to happen, because when you put sodium hydroxide in it, sodium does not, the sodium ion does not recombine with hydroxide to make NaOH. Because it's a strong base, this reaction only goes this way, and we only use a one-way arrow. You can't have sodium recombining to make NaOH. So if the ion would become a strong acid or base when it combines with water, then it is not going to happen. That combination won't happen, and it will not affect the pH of the solution. I think we got just one more example. Chromium nitrate is our last example here. Let's look at that one. So this one, our salt is CrNO3. So when this salt dissociates in water, which it will because of the presence of the nitrate, it'll make a chromium 3+ ion and 3 nitrate ions. As we've discussed, the nitrate will not recombine with hydrogen from water because nitric acid will not recombine because it's a strong acid. But the chromium does have the potential to interact with water. In the presence of water, Chromium can pick up hydroxides, and it would pick up 3 of them because it has a +3 charge. And that would leave behind some hydrogens that are by themselves. So if you put chromium ion in the water, it is going to increase the concentration of hydronium, which will decrease the pH and which will make the solution acidic. I say the simplest way to summarize this is that if the cation, like the chromium that we just looked at here, is the conjugate of a weak acid or base, would be the conjugate of a weak base, then it will make the solution acidic because it's a conjugate acid. If the anion, like this acetate or this nitrite here, if the anion is the conjugate of a weak acid, like nitrous acid or acetic acid, then this conjugate base will increase the amount of hydroxide in the solution and make the solution basic. So this says if you found a solution of sodium nitrite in a chemical cabinet with an unknown concentration, what measurement could you take to determine the concentration of the salt? Would this technique work if the solution was sodium nitrite instead of nitrite? So I've got copied down here the equations that we wrote on the previous slide. First, the salt would dissociate completely, 100%, into the sodium ion and the nitrite ion. Then the nitrite ion would have an interaction with the water molecules to make a little bit of nitrous acid and increase the concentration of hydroxide in the water. That means that the solution is going to be basic. And that means we could measure a pH. So if we got a pH, we could use the pH to figure out the concentration of hydronium, which we could use to figure out the concentration of hydroxide. And since the stoichiometric amount of HNO3, OH, and NO2 are all the same, the concentration of OH would be equal to the concentration of the nitrite ion, which would then be equal to the original concentration of the sodium nitrite. So that means we could figure out the concentration of the sodium nitrite by figuring out the pH, using that to figure out the hydroxide concentration, which is then the same as because it's all 1-to-1 ratios, 1 to 1 to 1, back to the original 1. We could use the pH to figure out the original concentration of the sodium nitrite. However, it says, would this technique work if the solution was sodium nitrate? No, it would not, because neither the sodium nor the nitrate ion would have any interaction with the water molecules that would change the balance of hydronium and hydroxide. Therefore, no matter how much sodium nitrate you put in, the pH is going to stay neutral, and you could not use pH to determine the concentration. So you can use pH for a salt that contains a weak acid or base in it, but you cannot if both species are conjugates of strong acids and bases. And last but not least, we've got to talk about how to do calculations, although the concept is very important to understand first. So we've got a salt. I know it's a salt because we've got a cation, we've got an anion. It doesn't look like an acid. The presence of the sodium indicates it's probably going to be a salt here. And so when we put a salt into water that has a species that's going to make it soluble, sodium in this case, it's going to dissociate completely. Therefore, I'm using a one-way arrow, not a two-way arrow. So this is going to dissociate into sodium and HCOO minus. And I know what that other species is because, I recognize the sodium. And I know sodium is always plus. Therefore, everything that's left over must be the anion part of this ionic compound. The sodium is the conjugate of a strong base, so it is not going to recombine with anything from water, but the HCOO minus is the conjugate of a weak species, so it will interact with water. And notice I'm doing a double arrow here because this is a weak kind of interaction where not all of it will recombine with water, but it will make HCOOH, so it's going to take hydrogen from the water and increase the amount of hydroxide. So this tells me right away I'm expecting a base. So I'm expecting a pH at the end of the day that's higher than 7. So we say, it says a solution that had a concentration of 0.24 molar. Well, let's just take it through and double check the stoichiometry. We've got, for every 1 mole here, let's use a pen. For every 1 mole of the salt, we get 1 mole of HCOO minus. Therefore, the concentration of the salt and the initial concentration of the anion are both going to be the same. So it'll be 0.24 molar. So I'm going to use an ice table here. Not worried about the water because it's a liquid. So we're going to do minus x plus x plus x. Now I'm going to set up an equilibrium expression. But I'm given the Ka of HCOOH, which is the product here. I need the Kb of HCOO minus. Well, you may recall the Ka of a weak acid times the Kb of its conjugate base. Multiply together to give the equilibrium constant of water. So the Kb, because we want to use the Kb here because we're generating hydroxide, because we're starting with a base, the Kb is going to be 1 times 10 to the negative 14th divided by the Ka that we are given, 1.7 times 10 to the negative 4th. And I'm just going to leave it like that for the sake of this problem. So I'm going to write this Kb expression in terms of our chemicals in the reaction. So it's going to be the products, x times x, which is x squared, over the reactants, 0.24 minus x. And it's probably going to be a safe assumption to neglect this x, because when we take negative 14 divided by negative 4, we're going to get something like 10 to the negative 10th, a very small number. So it's probably going to be safe to assume this is a very small amount here. So I'm going to do some algebra and solve for x. At the x is equal to 3.8 times 10 to the negative 6. Certainly very, very small. I think I can say with confidence, even without doing the math, that something that's 10 to the negative 6 is less than 5% of 0.24. So I feel pretty good about my assumption. Now x, going back to the problem, x is the concentration of hydroxide. So this is our hydroxide concentration. And so I can get to the pH in a couple of different ways. I decided to figure out the pOH from the pH as negative log of this number, which is 5.4, and that makes sense. I'm expecting something around 6 because the exponent is 6. So the pOH is 5.4, and I just take 14 minus 5.4 to get me the pH, which is 8.6. And I am expecting something that's basic, that was a pH above 7, so that matches my expectations and seems like a reasonable answer for this problem. So after watching this video, you should be able to look at a salt and identify if the salt will impact the pH of a solution. So will the salt be neutral, or would it make the solution acidic or basic based on the cation and anion that the salt dissociates into? You should also be able to calculate the pH of a salt if you know its concentration. And based on the work we've done with weak acids and bases already, if I gave you the pH of a salt solution, you should be able to work backwards and figure out the concentration of the salt.